All right, so this lecture is going to give a very brief introduction to the topic of photochemistry with an application to the stratospheric ozone layer and what's known as the ozone hole, which hopefully many of you have heard about at some point in your life. So the reading, there's a few different readings in Aaron's that I recommend, since obviously in this class we're really only going to be able to touch on atmospheric chemistry relatively briefly. This is a movie showing the evolution of the ozone hole from 1979 to 1999. So in Dobson units. Okay, so learning goals. The first goal actually, so I've shortened this lecture, so the first learning goal is really covered more in the extended notes that are posted on Blackboard. So here I've really tried to trim this down just to give you some basic intro to the notion of stratospheric ozone and ozone chemistry. But so in the notes describing the basics of chemical kinetics, chemical production, and loss, and we talked a little bit about that before in the concept of a box model. And here we'll describe briefly how sunlight can drive chemical reactions in our atmosphere, and then explain what creates the ozone layer and why the ozone hole, in quotes, formed, what that is. So when we talk about the concept of photochemistry, what that is the So here we're going to learn about this concept in the context of the ozone layer in the stratosphere. So we'll talk about its formation and depletion. So what is the ozone layer? So this graph on the right shows on the x-axis is ozone concentration in parts per million as a function of altitude, and the y-axis in kilometers on the left side there. So you can see in the troposphere, the concentration of ozone is pretty low at about 1 part per million. Though as you learned about last week with Professor Prabhakar, is that this ozone, we can produce ozone photochemically in the troposphere that can create pollution and smog, so it's very important for different reasons. But then meanwhile, up in the stratosphere, there's a peak in ozone concentration at about 25 kilometers. And so in general, the stratosphere contains about 90% of all atmospheric ozone. So to note the total column ozone, we use these funny units called Dobson units. So total column ozone might sound a little bit similar to total precipitable water, and it's very similar in concept. So here you're not literally precipitating out ozone, but you're thinking about if you look directly overhead in a column of air, 1 Dobson unit is equivalent to 0.3 centimeters thick layer of ozone at 1 atmosphere pressure. So it's an ideal gas of pure ozone. And so on average on Earth, we have about 300 Dobson units of ozone in the column. And again, 90% of that is in the stratosphere. And so again, the maximum concentration of ozone, so O3, I haven't said that yet, is about 12 parts per million at 25 kilometers. And that's on average over the course of the year and over all of the Earth. So why is the ozone layer important? It protects life. So this is just a schematic of what the ozone layer is doing in terms of its function for life. As a UV photon comes in, an ultraviolet photon comes in from the sun, and it hits an O3, an ozone molecule, here with 3 ozones shown in red. And that causes that ozone molecule to dissociate, if it's at the right wavelength, into an oxygen molecule, O2, and then an atomic oxygen, O. And so this is written in terms of a chemical reaction form as O3 with the right arrow and H nu, indicating, again, this is not a molecule, it's just a photon coming in, so it's just energy added to the system, and it dissociates to O2 and O. And you can see that this requires a photon with a wavelength at most 340 nanometers. So again, you need relatively high energies or short wavelengths. Okay, and so what does that mean for us is that ozone is the only major atmospheric constituent that absorbs significantly between 210 and 290 nanometers from the sun. So this is incoming solar radiation here. So remember, visible starts at about 400 nanometers, so just off to the right. So here we're in the ultraviolet range, so more violet than visible violet light. And so in the red line shows the incoming solar radiation as a function of wavelength, and the y-axis is energy intensity, so you see joules per meter squared per second. That's just joules per second is watts. This is just watts per meter squared coming in at each wavelength. And so you can see then in the blue curve shows that same energy flux coming in at the surface. So the difference between the red and the blue line is what gets absorbed or scattered back to space by the atmosphere itself. So you can see is that at above 320 nanometers, most of that solar radiation is making it all the way to the surface. But then when you get to shorter wavelengths and higher energies, when you get below about 300 nanometers, now almost all of the photons are being absorbed within the stratosphere. And so basically the ozone layer is like a big layer of sunblock for life on Earth. So note there that without it, life would have likely remained underwater. If you came out, you would incur significant negative impacts of these high energy photons hitting your skin. Okay, so when you talk about the ozone hole, it's defined really as a region over Antarctica with total ozone of 220 Dobson units or lower. So again, the average is 300 Dobson units. And this is an example shown in September 2005 from NASA, and you see it's significant over Antarctica and kind of spreads towards or equatorward from the South Pole in particular. And so this is what we refer to as the ozone hole. It's just an indication of a significant reduction in ozone. And so just as an example, so we pointed out here this is in September, so this is really prominent. This ozone hole really emerges suddenly as a marked depletion of ozone. Here shown a loss of 50% or more of total column ozone in the lower stratosphere over the Antarctic in the weeks after the spring sunrise. So again, emphasize the spring sunrise. So something is happening here where when at these high latitudes in the southern hemisphere, when the sun rises for the first time after polar night, so there's been no sunshine for a long time, suddenly these high energy photons are once again bombarding the stratosphere. And there's a pretty marked shift that occurs. So what's shown here, this is in units of ozone partial pressure. But you can just see on the as a function of altitude on the right or pressure on the left. And so this is showing the changes within a given year of ozone concentration or ozone partial pressure between late August and early to mid October in 1986 and 1987. So you can see there's this huge drop. And that's something that commonly occurs. So independent of any influence, there is this reduction in ozone at this time of year.
Now, what you need to understand about the ozone layer is that it's not just ozone. In the upper atmosphere, some pretty funky forms of oxygen can exist, not just the O3 ozone molecule, but also atomic oxygen and the usual diatomic oxygen that we're used to seeing at the surface of the Earth. And all of these species are in equilibrium with one another, meaning they interconvert between being an O3 and an O and being two O2s. So what's really going on here is this constant interconversion back and forth. But it always leaves a little bit of ozone there. You notice that in this equilibrium there's always some O3. And that's good news for us because we need that O3 there. Now, the problem that comes with the use of chlorofluorocarbons is that as they reach the upper atmosphere, they change that equilibrium in a way that doesn't suit us very well. So, the normal healthy equilibrium involves atomic oxygen and ozone in equilibrium with diatomic oxygen in a reaction with this kind of stoichiometry. O plus O3 goes to 2O2 and back again. But what happens in the upper atmosphere? When we allow something like, in this case, Freon 12 here to reach this ozone hole, which I've shown here in this NASA photograph, showing it over the South Pole. Well, what happens when chlorofluorocarbons get up there is they act as a source of chlorine atoms. And that's what gets the reaction messed up. It's the presence of that chlorine atom which catalyzes the breakdown of ozone into O2. So this equilibrium gets thrown out of balance because the chlorine atoms accelerate the decomposition relative to the reformation of ozone. And that's going to mean that the ozone concentration, where there are chlorine atoms, is going to go down. Now, what you need to understand about the ozone layer is that it's not just ozone. In the upper atmosphere, some pretty funky forms of oxygen can exist, not just the O3 ozone molecule, but also atomic oxygen and the usual diatomic oxygen that we're used to seeing at the surface of the Earth. And all of these species are in equilibrium with one another, meaning they interconvert.
And so this cycle is what we call the Chapman cycle, and it really governs the mass balance of stratospheric ozone. And an important aspect here is, again, this is driven in both directions by the absorption of high energy photons from the sun. So, and there's more details about this in the extended notes if you'd like to see the chemical reactions associated with the Chapman cycle, but we just won't have time to go over that here. So what's important is, as mentioned in the video, is that that human activity, as well as other natural sources, can introduce catalysts that can accelerate the destruction of ozone, of O3. So catalyst, going back to basic chemistry, is a molecule that accelerates a chemical reaction but doesn't actually get used up necessarily. Well, it can be, but it's often not even used during the course of the reaction. It just simply helps to accelerate it. And so there are 4 families of chemical species that act as catalysts for the destruction of ozone in the stratosphere, which is nitrogen oxides. We often refer to as NOx, NO with a sub X, so that's NO or NO2. Hydrogen oxides, HOX, so that's actually, we often write OH instead of HO, which is the hydroxyl radical, as well as HO2. And then chlorine, which can be just an individual chlorine atom or chlorine with an oxygen. And then bromine, similarly a bromine atom or bromine bonded to oxygen.